All right, second part of center of mass. And this time, we'll take the lamina, which is 2D, and try and extend that to 3D bodies. We call it the uniform body, and really an extension of the concept of what we did in lamina. But let's first of all kind of visualize. I think everybody, you would have seen a ball, a sphere, center of mass right at its center. Similar, just as if you had a circle, its center would be its center of mass. So if you extend that idea, there's a few things you should remember, and I'm not going to write it down, but I think fundamentally try to intuit that just as you had lines of symmetry on a lamina, here you could have lines of symmetry and you can also have planes of symmetry. So if you took a sphere, obviously you'd have an infinite number of lines of symmetry through which you're basically passing through its center, right? You could draw infinite diameters on a sphere. Likewise, each of those lines could have an infinite number of planes, but the center of mass is where all of these, would intersect. So all planes of symmetry and all lines of symmetry, effectively, or axes of symmetry, intersect at the center of mass. So it's very easy on a sphere to understand that. But if you had a cylinder, a completely right circular cylinder, essentially meaning its two faces, its two circular faces were perpendicular to the body of the cylinder, then you would also have the same argument. Its center of mass would be along its axes, bang in the center of those circles, right? Those two faces, and that would be the axis of symmetry, and an infinite number of planes would pass through that axis of symmetry, and the center of mass is basically on it. So you have this fundamental idea. Likewise, you have a cone. If it was the right circular cone, it'd be the same thing. But I want to now take that example of a cone and just extend it a little bit and say, hey, what exactly happened? And if we draw our axis here, right, and I'm gonna use this cone as an example, and then you can stretch your own imagination with everything else. And I'm gonna say, I'll make an attempt to draw my my cone. Right? So that was sort of my cone, and somewhere here, again, I'm hoping that my color choices are not too painful. They are painful for me. I'm hoping they're not. Right? If I just made that as my cone, and I want to visualize these, when I find these kind of objects, it's a lot easier to say, what's going on, because I kind of define, I know that there's this axis of symmetry, but if I obviously looked at it just from the side, I would actually be, what I'd be looking at is that. Is it not? It was just that, right? It's almost like saying, I've now taken this triangle and I've spun it around the x-axis and I've generated this cone. So it's this two-dimensional lamina that's been spun, and that's the idea we want to take. Right? What we want to take is to say, if we have a lamina like that, can we take a slice of this, a tiny slice of this, that then acts as a disc, right? We take a tiny slice of this. It acts as a disc, right, of thickness. I'm not, skip the delta x. You guys are integration students. I've got my dx there, and now I have a circle, right? So the area of that circle, and obviously this is y and this is x, right? This is the axis. So I've got my x and dx there. The area of that circle can be written as whatever is the y. The area of that circle is pi times y squared, which means the sort of the volume, if you will, is pi times y squared dx. and the mass would be times its density. So now I have an expression to write the mass of this tiny piece. So I hope you're with me. I've defined a y because I can write this as a function each side, actually just one side, not two sides. Y is equal to f of x. Right? Obviously, in this case, it would be R and H. We know that. It's a very simple case that I'm making, right? But now I'm not doing a y here and a y with a negative slope here. Not doing that. I'm just doing this y, but I'm flipping it down. This is my radius, as y is equal to f of x. Pi r square is giving me my area of that circle, giving it a thickness of dx with to get its volume with its density to give me a mass. The mass of that tiny mi. And because of symmetry, I can always say that for yi is equal to 0, because I'm spinning it off the x-axis, right away I know that. And I know xi. Xi is there, is basically the xi. Xi is x here, right? So I could now write my mass as an integral from 0 to h. That's h. And that's r. Gee, I hope you can see it. Let me check. Yeah, visible, right? So I can write this, 0 to h. So my problem setup for mass, and you should get this automatically, right? My problem setup would be mixi, which would really be rho pi, right? Y squared, which is function of x, right? Times x dx, 0 to a value of x, whatever that is, divided by same 0 to a value of x of rho pi y squared dx. I hope you get the logic here, right? The mass with the center of gravity, and obviously y is 0. This is applicable as long as I've taken a two-dimensional object and I've flipped it down 360 degrees to get a pi r square for my radius. This works just fine. I can do that with the cone. I can do that with a cylinder, because for a cylinder, all I'd be doing is taking this one rectangle and then just having it spin 360 degrees about that axis. So if this is my axis, very easy to spin it, and then I can define what will be my cylinder. And obviously, if it's a cylinder and it's a uniform, meaning its density stays, they're all uniform bodies, so their density is constant. You can also use the cylinders for this kind of a cylindrical object. You can use it as a function of length, and that's when it's called a uniform rod, because I'm not looking at the area, I'm just looking at the length, because that doesn't change here. Area is just length r squared, length pi square length to get the surface area, so that pi square r, that's constant across all lengths. Here the pi r squared is not the same, it's pi y squared, and that changes. Here it doesn't, because here y remains constant. So you could do the same model, you could get the same result, you get similar results here, right? So this is an important idea, I think, that you have to work out when you set up the problem. Again, it's the problem setup and defining this equation that makes a difference. You could have, and again, the formula sheet has several equations that ask you to prove in different ways how your approach would be for these, and in some cases in the exam, I believe they also ask you to prove what would happen. Sometimes they give you the formula saying, oh, here's the right circular cone, its center of mass is I believe that say it's 12 by something from its base, and they might give you this value here, and in some cases they might ask you to prove this value, in which case you would take this function, set it up this way. Again, understand this is the total mass, right? Rho pi y squared dx, total mass, that's the integration, 0 to x, or in this case 0 to h. If you want to call it h, it's up to you, but I'm just using 0 to x, right? And then set yourself up to the small one, which is rho pi y squared dx times the center of mass of the unit disk, and 0 to x. And again, depending on the solid, depending on the setup, you might have to make sure that you get your limits correct. It could be an x equal to a to x equal to b, or any variant like that. This problem becomes quite interesting in multiple ways. One of the ones I personally like are when they tell you, or they give you a cone, and I'll just stick with the cone just to give you an idea of what is going on and how you should treat it. They can give you a cone, but they will give you a truncated cone. So now I'm going to truncate this cone here and ask you to just find the center of mass in this space. So the truncated cone would be something like that, right? And I've removed this part. So it's no longer a full right circular cone. It's basically a truncated cone. When you reach a situation like this, if you're asked to do it algebraically, or rather, if you're asked to do it using calculus, this is merely a limits change, alteration of limits. You would do the exact same integral function, but your limits are no longer 0 to h. It's whatever this value is, to h, right? That's the limit. So limits problem's easy. But you also have another approach to do, and that's the approach of moments, where I take, let's say, I cannot handle that color. I take my net mass, and I'm using the word net, right? And I set it up again as a moments problem. So my full cone, this is my full cone, and its center of mass, which I know from a formula sheet, and I subtract from it the missing cone. I'm just going to call it M. These are all just my own notations, right? And that's a setup as a moments problem. And typically what happens is, because a lot of these are geometrically similar, you will see that you can create a small table, right where you work, say shape, and you can say here full cone, missing cone, and then net. And then you can write here mass, and this is nothing but Mn. You can, you may not know what the value would be, or you could just kind of guess the value because it's a subtraction. You'll know the full cone because there is a formula for the mass of the full cone with its density times the volume of a cone. You can write that, the volume of the full cone, right? Check your formula, do the math. You can similarly write one for the missing cone, and then you can subtract it and get the net cone's mass. You have the mass function. You can also get the xi, or the x bar for each of them, right? And again, there is a formula for it. It is not coming straight into my head, but I think it's something to one of the pi factors, 12 by 7 or something, pi r squared h or something like that. There's some factor like that you will get, and then you can write those two down, and you will just see that if you apply the ratios and equate it, you'll get your x factors. You can do it in a shortcut. So I like the fact that they give you this truncation, build a table out, and hopefully you can set yourself up. But the key is whether or not you have the formula. If you attempt to do these algebraically a few times, you'll be at ease doing the algebra. Calculus. Not you'll be at ease doing the calculus, because there are exam problems I have seen where they'll ask you prove the formula that the center of mass of a cone, a right circular cone of height h and base radius r is equal to 12 by 7 pi r square h, for example. And then you're going to have to figure out how to manipulate, I think it's 12 by 7 h pi r or something like that. And then you have to do this. So if you do these a few times, the formula sticks in your head, much easier to go back and forth your formula sheet, and if you do get a problem, you can do it. And that's just one example. I can have if I have something like this. So here's another case, one of the classic ones they ask you, right? And that is a shape they give you of a bell or a funnel, and they say it's right circular, and then you have a function here. It is exactly the same thing, except that it's not a straightforward r by h and y is equal to r by h x. Is here y is equal to f of x. They specify it as a function for you, and usually it's not an overly complicated function. Sometimes there's an exponent, but once you get that, you've gotten it in the concept of there's my disk, there's the thickness of the disk, and there's the volume. Then it's purely an integration, right? Because the y square function, the pi y square, so pi comes out, the density comes out, so it's just a y square different integration problem, which is fairly straightforward. So I think these are easy to get, very common. They like to give you these problems, and of course they combine it with other more fun, interesting things as well, and we'll get to that in just a second. But the next idea when it comes to three-dimensional objects, I think I've covered the setup. So again, this is not, I don't want to teach integration, but this is the setup. But what I'm also going to do is kind of extend the three-dimensional object into a case where you can have a three-dimensional object where its density is not uniform. So all of what I did up until now, when I set up this problem, x bar and m, the total m, and I wrote that as my summation of xi mi, I very conveniently kept canceling out my density. Here, they can challenge that for you. They can give you density as a function of x or y. You've got to watch out. And a classic case of that, right? And you can think of it this way. A classic case is a pole, a wooden pole, and often it's taken off a tree, and it's not of uniform diameter. Neither is its density uniform, right? Often the older part of the tree is much more dense, so neither is the diameter nor is the density. Well, then you will get a density as a function of x, where that is x. So what happens to this problem? Again, I want you to set the problem up correctly, right? If you set the problem up correctly, you will solve it, because the integration is a breeze. What will happen here, now two parts, remember they're all integrated separately. So if I extend this, my x bar was a summation. Actually, time to throw the summation away, because I think integration is not a challenge here. So my x bar here is the integral from a to b of So I have two integrals that are working here. I have integral a to b. Now what was I doing? I was defining a tiny disk, right, of some area. That area was a y, if I used a y function or whatever I used for it, but this time, however you define the area, observe what happens. I'm still having my pi because I'm still spinning it. It's a pi y square. Let's say I set it up this way with my dx. But now I'm multiplying with density. Density is a function of x. So I might not have much of y changing with dx. I might be able to write this as pi y square, because y square is typically out because y is constant, right? If this is just let's say it's a uniform, if the diameter doesn't change, right? If the diameter doesn't change, then I can bring my y square out, and then this would be just the integral of density dx, a to b, right? That's what this would turn out to be, right? But let's for the purpose of keeping the math challenging, let's just say y is also a function of x, and so is this. So you have two functions of x that you need to be mindful of. But what happens here? Here now this becomes, you get your pi, you get your y, which is a function of x, you get your density, which is a function of x, and you have your x, remember that, times dx. So your function, your math increases. So if y is not a function of x, you're safe, they come out. Then it's just density as a function of x times x dx, and it's density a function of x dx here. So that's the setup of the problem. So you figure out how you set the problem out. And I've done this now with x. You could do this in y, you could do this in any dimension if you do, but obviously the relationships don't change. If it is y, then you apply the same logic. Principal idea is we took the y coordinates and we took the center of the two y coordinates to get, so you would define that as the y for the y bar here, right? So you'd be careful, it's not just putting y, but it's the yi, so you would be careful with that, right? The mass factor doesn't change. So hopefully that kind of addresses a varying density problem, right? This is something that you have to keep in mind. Now, the last part, I think, of center of mass for three-dimensional bodies. So we did uniform bodies. Now we did non-uniform bodies with density as a function of a dimension of size. Now we have a composite body which effectively is not uniform. And that happens when, let's say, I have a case where, let me go back here, just an example. I have a case where I have a solid, and this is just a section. I have an object of this type, right, which is a hemisphere, so it's half of a sphere, so it's cut down. And right on top of that, I mount me my favorite, like a cone, right? And their radii are the same. But if the cone is different, actually, you know what gives me, yeah, if they're of different, let me make something more relatable. So you buy an ice cream cone, right? This is effectively just, very thin paper-like material on top of which we mount, let's say, a big, dense scoop of ice cream, right? A dense scoop of ice cream sits on top of this. Let's say such that this is a hemisphere, right? And it just sort of sits at it. What would happen to their center of mass? Well, the way you would do this is, because their densities are different, I have two objects here. I have a solid object here, and I have a solid object here, two bodies. I would go back to my moments problem. So first use a formula. Now you know for a cone they're along the axis of symmetry for the whole thing, right? You know that for a semicircle, it is, I believe it's from the top, or from, it's 2 by 3 r, and then for a cone I believe it's from the base, I think it's like 5 by 7 something of h, or the factor like that. So you have this value, right? You can calculate their mass. That you would do the exact same thing, mass of the total object, which is just the numerical sum of the mass, which you know. The x bar of the total is equal to x bar of the ice cream times mass of the ice cream, which you know, half of a sphere. You know the volume density of the ice cream is given, plus x bar of the cone alone, right? I and C, so the cone alone, which you can again find out in the formula, and mass of the cone, which you know again, volume of a cone times density. So you have two different densities, right? And that would be more simply written as mt is equal to mi plus mc, and then each of them, mi is equal to density of ice cream times volume of the ice cream, right? And m of cone is equal to density of cone times volume of the cone. So if you get these ideas and you know that by formula, much easier, which is why I'm suggesting, and likewise for xi and xc, I'm suggesting you do these things manually by integration on the uniform three-dimensional body. So the formula sticks in the mind, so that when you see a problem in the exam, you're not wasting time attempting to do integration or any calculus or anything like that. The formula appears to you, validated in the formula sheet. Don't, because sometimes you can forget. Validate the formula sheet. You know the volume, you get the density in the question, you get the mass, those are done. You know the formula for center mass of hemisphere, center mass for cone. Plug it in, add the mass very easily. So much easier to get this. Very, very easy. You can do this problem in 5 minutes, or you can do this problem in about 25 minutes if you didn't remember what these values represented. So anyway, that's my sort of conclusion on the center mass for three-dimensional objects. Basically, I kind of gave you how the integral equation is set up, and then discussed possibly where the density is function of x, so the integral equation set up differently. And then finally, I also wanted to talk about the sort of composite type, where you have two different types of objects. And they like these problems very much because they really want to test whether you know your concept well. If you know your concept to the dot, then you can do this super easy. And you can often see this on an exam where your question only kind of has like 5 or 6 lines, and it's a 3-mark question. You look at something like this and go like, oh man, the amount of working I'll need to do if I didn't know these. So keep, bear that in mind. Do them algebraically. I think they'd be really nice. So okay, before I leave two-dimensional three-dimensional bodies, I also want to just use the same time, because I saw a hemisphere, and just give you the same idea. You can again do the math, right? So I talked about, so supposing I have a hemisphere. Somebody give me new chalk. So I have this sort of hemisphere here, right? And again, we can identify that this hemisphere is basically this circle, the quadrant of a circle, flip 360, and you can do the math that way to get the problem setup to get its area. You do that one way, right? Do that one way. The other way is do a problem setup of, so first problem setup is just this y square, right? You basically take the slice here of the hemisphere dx and then integrate 0 to r, right? So that's one problem setup, right? Where you know this equation. You can also think of it from another perspective, and you can do this as if this was my center, I can take a tiny piece here, right, along that sort of band, see what that semicircle would be, semicircular strip, if you will, in 3D, and then do the integration with theta from 0 to 90, or theta from negative 90 to positive 90. Shouldn't say 90, say negative pi by 2 to positive pi by 2. Again, because you will see the factor in cosine is a negative sign, and then the negative 90 comes in on the negative sign, which will cancel the negative out. They all add up, and you'll get the answers. They're pretty beautiful integrations. Two integral techniques to do it, and I encourage you to do both. And your third sort of approach to it, if you want to still take this problem on, is to do the same thing, but flip this the other way and do this in y and see what happens. So these are some approaches I'd like you to attempt to do, and I think they're all very beautiful. Now, I also want to give you one more final task to consider. Supposing I have this hemisphere and this hemisphere with the radius here of r, and now I tell you that instead of the solid hemisphere, I want a hemispherical shell. And in this particular case, when I give you a hemispherical shell, in reality what might happen is I might not be asking, if the problem in the exam says use calculus to determine it, then you have to use calculus. You can set up a theta and a delta theta and take a strip there and take that little circular strip and integrate for theta and get the answer for the hemispherical shell, because this would be an extremely tiny strip that is just like a semicircle, and then you're just adding that up along theta, right? But your other approach is, if you already know that for a hemisphere, my center of mass is typically, let's say, 1/3 the way is here, right? If I have that idea, then you could define this to be mass times, or rather hemispherical, and I could define a second hemisphere. So this is one, if this is one hemisphere, I can define a second hemisphere right, of diameter d, and I can write this equation this time as my x bar of shell times mass of shell would be equal to my x bar of the main hemisphere with its mass minus the x bar of moments problem can be written this way, because their center of gravities with moments about the origin point here would give you this equation. Likewise, mass of the shell is nothing but mass of r minus mass of d. If you know those values, you can, and you'll know, because you have density, you have pi r cubed, 4/3, 2/3 pi r cubed for volume. For a hemisphere, pretty much it's the r cubed, which is here r cubed and d cubed. So you'll see how they subtract. You can know the formulas. Here it's 2/3d, 2/3r. So you have an r minus d, and then you'd have an r cubed minus d cubed that would appear. Again, play with the algebra a little bit. You write your r cubed minus d cubed as r plus d times r squared plus rd plus d square. You take out your r minus d component as d approaches r, so that the r minus d, the 0 goes away. And then you can solve it again, and you will get the answer for a shell. And I think the answer should be 1/2 r, right? That should be the answer. But you can do the math yourself. Again, very nice way, not using calculus, but just knowing the formulae of this. Very quick and easy means of obtaining that answer, right? Because if they don't ask you to say, hey, use calculus, it's a 2 or 3 mark question, you use this method and voila, the answer is there. Unless they insist you have to use calculus, in which case you take the little, semicircular strip with the theta and perform your integration. So I will leave you with that. I think I've kind of used up a good amount of time explaining center of mass and all the applications of that for 3-dimensional bodies, uniform, non-uniform, and composite bodies. So lots of problems, nice math, lovely integration work, and I'll see you in the next video.